Good afternoon, I'm Giuseppe Tiberti, and I'm working with Professor Plizzari at the University of Brescia. Today I'm going to introduce you some structural application of fiber-reinforced concrete that has been simulated with Diana. Before starting and going in details on the simulation with Diana and what we have developed here at the university, let me briefly introduce the research group. Several research are ongoing at the University of Brescia, to be honest. Today I'm going to briefly introduce the research group led by Professor Plizzari, which is developing this research group a noticeable research concerning innovative cementitious material for use in structural application. This research group is currently composed by Professor Plizzari, is a full professor, Pastor Minelli, that is an assistant professor, me, Giuseppe Tiberti, that I am an assistant professor, and several PhD students as well as PhD fellows. So it's a very long list of students that are fundamental in helping us in carry on the research. I want to mention that the research on innovative material includes the research of typical innovative materials, that is fiber-reinforced concrete. This research in the last 2 decades developed by Professor Plizzari in this group was quite important because this research becomes a kind of contribution to specific rules and recommendations that are currently present in the section devoted to the design of FRC structure of a new model code 2010. Among the innovative material in this investigation, presentation will be focused on FRC. Will be an introduction of what is FRC, and then very fast example concerning the research ongoing at the University of Brescia regarding FRC, by underlining that very often this research are carried on in 2 parallel ways: experimental research as well as numerical simulation, generate parametric studies, carry on and develop by means of Diana. Furthermore, I'm going deeply on the main issue of this presentation, that are the concepts that are necessary for including the fiber reinforcement effect in crack models that currently are using Diana, and then an example application that is very interesting because, of course, it's very difficult to make experimental tests on this application, that are the severe loads applied by tunnel boring machine, TBMs, during the excavation process of a lining of a tunnel. I'm talking about tunnel. Very fast, what is fiber-reinforced concrete? Basically, is a concrete. Here you can see several typical applications. Is a normal concrete where during the casting process at this concrete is added a fibrous reinforcement consisting in short or long fiber with different shape and made by different material, as you can see in this slide. If you check the literature, or here of course I'm letting you just some basic concept. If you check the literature, you can really recognize that generally referring to a fiber content less than 1%, that is the fraction volume of fiber, the main advantage related to the use of fiber is the post-cracking tensile concrete behavior. It is well known, in fact, that in the post-cracking branch, concrete basically is a brittle material, which exhibit a fragile behavior. On the other hand, as you can see in this picture on the right, by adding to the concrete fibrous reinforcement, you can change this brittle behavior in a so-called toughness behavior. This is very important because it enables us to have the chance to have a more durable material, to have a better crack control, and when also the fiber are used in combination with traditional reinforcement, you can have a considerable improvement of tension stiffening effect. And this is also important to fatigue, shrinkage, and as it will be dealt in this presentation, for the so-called disturbed regions, D regions, that are general regions characterized by the difficult to find a reinforcement that is placed exactly with respect to the principal stresses. With fiber, you don't have this problem because fiber are everywhere in your concrete matrix. Here the main effect, starting from the previous slide, that was a slide concerning one element under tension, the effect that by increasing more and more the fiber content, leading to a fiber content of 2% or 8%, you can have also a material that is, from the post-cracking uniaxial tensile point of view, a kind of strain-hardened material. So this is a good fiber-reinforced concrete, which is on the right. There is a very, very good fiber-reinforced concrete with high amount of fiber that becomes a strain-hardened material in terms of tensile strength. One of the key issues that is very important for people or design is to start from the material level and go into the structure. And I can tell you that in this step, from material level to the structural header, also Diana and the numerical simulation plays a relevant role, and so are very important. In fact, generally in traditional reinforced structure, I'm telling you, concrete plus traditional rebars, as you can see on the left, you can use a well-accepted linear behavior up to the yielding up to cracking, and then you have also a linear behavior. You can, as a first approximation, use up to the yielding of traditional reinforcement, consisting in rebars. In FRC structure, it's different because the properties are in the post-cracking behavior. So you need something that is going on non-linear behavior. And this is, can be found, for instance, in Diana, as I'm going to explain in the presentation, by means of the concrete crack models that are included in Diana. Just for people who are involved on micromechanical approach, this slide is just a flash. There is a long discussion about it. This slide is only about how the fiber-reinforced concrete works in terms of mechanical point of view. Basically, the global effect is the sum of two effects. From matrix of concrete, that is on the right, that is going down a Britten magna, but at the same time, fibers start to work, and so you got toughness. This toughness is very important. Generally, from design point of view, I underline this because the starting point of the use of Diana was also this. Generally, you can carry out a uniaxial tension test in order to evaluate the post-cracking behavior, but are very difficult to carry out, and so generally people carry out so-called indirect tensile tests that are flexural bending tests. Even in this test, it is possible to achieve, it's possible to obtain the constitutive law for use, as well as in analytical approach, as well as in numerical analysis. This is a typical example of a notch beam, where you force a notch, so you got a crack, and you get a diagram, for instance, like this one, and then you have two possible ways to use very simple nominal residual post-cracking stress, or, as we are going to see, to use more advanced program like Diana in order to analyze this diagram and get back your uniaxial post-cracking tensile load to be used in numerical simulation. Before going to Diana and to tunnel lining, basically, I want just to underline the possibility in terms of research that has been already developed and has been already used in our university. So are several pictures concerning the research ongoing of FRC. Here we got a masonry structure that has been reinforced, as you can see on the left, by means of a mortar coating made by steel fiber reinforced mortar. Here there is the test. Parallel to the test, there is the numerical simulation that is being developed with Diana. In the same way, you got a so-called underground water tank, and here the numerical model of Diana. This is a typical way to work that we have at this university, and we have used in several research. as well as this is another research ongoing. For instance, today another thin plate is going to be tested, and then it will be, of course, simulated with Diana. Here we got the test, and then we got the simulation. Furthermore, there are also other research where the tests are very difficult to carry on. The example of these are the slabs on gray under shrinkage effect. You can imagine that by developing a full-scale test with a big slab under shrinkage effect, which means that the test should be carried out in a well-controlled environment, is very difficult. And in this case, Diana helped us because we can control the environment very easily by means of numerical simulation, and so we can study the effect of shrinkage under slab on grade. And you can see if people are involved, for instance, on these issues, you can say that with this, of course, enlarged deflected shape, the so-called curling effect typical of slab due to a differential shrinkage within the thickness of the slab. And then we have also here pipes that has been simulated once again with Diana. And then we can go on the topic of this presentation, that are tunnel lining. Here at the University of Brescia has been developed a national research project, so national it means here in Italy, concerning the possible use of fiber-reinforced concrete in so-called conventional tunnel lining, as well as on precast tunnel segment. This is the first conventional tunnel. It means that the tunnel are excavated by means of conventional method. And of course, here we want to see the fiber effect when the tunnel is loaded by the ground. And as you can see, we have made a mesh with also a proper mesh refinement in a very critical region, that is the so-called joint, because generally this first part of the tunnel lining is cast, then after a certain amount of days, the second part of the tunnel lining will be cast. And so there is also this peculiar issue. And then the topic of this presentation is precast tunnel lining elements. As you probably know from, I don't know the background of the audience, but as you probably know, several times currently the tunnel lining are constructing by means of this very big machine. In this case, also the machine has got a name. And this is called tunnel boring machine. The main idea is to have basically a big driller that is able to excavate the ground, and behind this big machine, a tunnel lining made by several precast tunnel segments is built. And here there is a quite complicated numerical model that has been developed with Diana in order to study an important phase during the construction stage of these precast tunnel segments. And now I will go to the material level, to the structural level. So it is necessary, before starting to the tunnel lining, so the structural level, it was, in my opinion, more than necessary to slightly introduce some basic concepts that are necessary and very important to introduce the material properties related to the use of fiber-reinforced concrete. These material properties should be, of course, properly described by Diana in order then to, at structural level, evaluate how this new material, innovative material, can influence the structural behavior. So I'm going to go a little bit slower, because our concepts that I will try to explain in more detail. As I mentioned before, the main advantage of fiber-reinforced concrete with respect to a traditional plain concrete, so a concrete without fiber reinforcement, as well or different type of fiber without any fibrous reinforcement, is the noticeable improvement of the post-cracking response under tensile behavior, because of a fiber effect. In order to include this contribution, it is obvious that we need to go to use non-linear analysis that should be able to describe the post-cracking behavior of concrete. And is why, in this university, we have decided I think it's almost 10 years that we are using Diana, because we started to use Diana with my first research fellowship. We have decided to use Diana because it is a well-known, very good final-headed program that has got several peculiar properties, but one of the most well-known peculiar properties is that it is able to have several, not one, several crack model. To be precise, we have a multi-directional fixed crack model, a so-called total strain fixed crack model, and so-called total strain rotating crack model. If you want to have more information, I think you should have to check the PhD thesis of Professor Jan Roth coming from the TU Delft University. As a general recommendation that comes from the background, I think, of each engineer, but sometimes is useful also to remind it, it's also better, if it's possible, to verify and validate a numerical model, because we know that the model are well implemented in finite element programs such as Diana, but it's also very important that the people who are working with Diana are able to properly make the properly choice of the several parameters that are included in a so complicated crack model. So the basic idea that we have developed here at this university is so very often to make a validation of the model with something that is available in literature, or, as I mentioned before, if the research program is able to have parallel to the numerical simulation experimental test, the validation will be done directly on experimental test carried out at University of Brescia. So, underline, very important, a validation of the model in order to check the parameters that are used in the model. As we mentioned before, for several engineers, material levels of fiber-reinforced concrete means this little and very straightforward experimental test, where you got a notch beam that is going under flexion, and here, where at this point now there are the LVDT, so you can see a certain characterize, and then you can have from your experimental test this global curve. This global curve comes from, in the real world, by a local behavior that concrete, that fiber-reinforced concrete, is able to exhibit at material level here, where the cracks is going to occur. So the concrete will be under tension, perfectly elastic up to reach the tensile strength, and then we can have a post-cracking behavior, uniaxial, that is being just schematized like this. From this local behavior, we got a kind of global behavior in this little structure that is the beam test. So the basic idea of a so-called inverse analysis method is, okay, I got the experimental curve, why not simulate this test by means of Diana, by means of two possible approaches, the so-called discrete crack approach. It means that we are placing interface elements here, or by means of smear crack approach. It means that you can have cracks everywhere, but it is Diana that understood basically that the cracks will appear here. And both approaches require to enter a proper parameter. Which is the proper parameter? Is the post-cracking law that is necessary to use inside your mesh, inside your simulation, in order to get this kind of numerical curve that should be as much as possible close to the experimental one. So it's a iterative procedure based approach that is well accepted in the literature. Here are typical results. As you can see, with this light gray curve, we got the experimental curve coming to a test like this one. Based on the experimental curve, we are also able to make a kind of mean experimental curve. And by means of an iterative procedure, by changing this constitutive law, which is implemented and which is introduced in the data file basically of Diana, we are able to get, by changing the law, the properly response. That is for us satisfactory. That is this one. This is the smeared approach, and this is the discrete approach. Why is satisfactory? Because sometimes the curve can be improved by changing the shape of a post-cracking law by bilinear law, as being used here, to a multilinear law. Because we know that Diana enables us to use also a multi-purpose, basically multilinear law. For us, this behavior from the concrete point of view is satisfactory because we got also a certain scatter even in an experimental test. So it means that the previous curve with this tensile strength, with this breakpoint strength, with this crack opening at the breakpoint, as well as with this ultimate crack opening, is the reference curve that is able, constitutive law, that is able to properly describe within the framework of Diana the FRC contribution. So by means of this constitutive law, we are able to say to the program we are using a fiber-reinforced concrete instead of a normal concrete. Afterwards, it is worthwhile mentioning that if it's possible, it is also recommended to, as much as possible, to test and to verify the Diana also with some of the typical loading conditions that you're looking for. What I mean, for instance, we have checked before starting our research concerning precast standard segments. We have also checked other type of standard tests that are the following: 4-point bending test and flexural test. These are typical standard tests. One flexural test on precast standard segments, so this is a portion of a segment under flexural test. And this is another type of notching test made by means of a 4-point bending test. I didn't have the opportunity to place the exact results, but I can assure that we were able to prove that the total straight rotating crack model with the opportune choice of parametria were able to capture the behavior that was found in the experimental test. But the thing that for me was very important to place is that since in precast standard segments I'm looking to describe during the construction stage when the TBM is pushing his arm on the previous installed rig, are in that stage, as I'm going to describe afterwards, very high concentrate force are introducing the lining, and a special situation, a special stress distribution occur, is well known in literature as splitting test. It's a typical test where you are introducing a quite high local compressive force within a small surface, and then the force has to develop, has to spread into a larger part of the element. If you want this concept, you can find also in the indirect tensile test that is called Brazilian test, for instance. It's a very complex state of stress, and so we were happy to verify this test that has been carried out during the experimental campaign carried out by famous professor that is Newton, as well this full-scale test on segment without curvature, both by very complicated stress distribution under the jacks, under the loads. And I can assure you that it's quite complicated to catch in the post-cracking behavior, as you can see, this particular condition. But as you can see, we were able, because I underlined this step just for time restriction. This is the experimental curve, and as you can see, even we were not able to have the same exact concrete used in this experimental research, because we get the result just from a paper. We were able to capture both the crack patterns and also more or less the bearing capacity. And so I think that this slide proves more than other slides that even in a very bad condition in terms of complex condition of stress to be described, we were able with Diana to catch the post-cracking non-linear behavior. So briefly, just 3 slides to say why in our research group we were interested to FRC precast standard segments. Because nowadays FRC has one of its most important applications in precast standard segments. I underline that are very big structural application, and in this application the effect of fiber reinforcement can be used and exploited very well. We got a non-toughness, smaller crack opening that is very important if you think that the lining is in the ground, so very aggressive environment. High resistant to impact loading, improved fatigue resistance, and so other thing, fiber reinforcement can substitute reinforcement along the tunnel. Of course, this is a very important issue for precast industry, for the factory who are producing these precast standard segments, and so we can reduce also the industrial process. So just to underline that besides the fact to be able to describe the non-linear post-cracking behavior of FRC concrete can be a very important question coming from the research community as well by designers. And it was important that when we started the research, I'm talking around 2006, we started for the first time the research concerning the use of FRC in standard segments. We were able to evaluate the opportunities offered by FRC, so post-cracking behavior, non-linear behavior, in an FRC precast standard segments, basically by means of the linear numerical simulation. Because, as I'm going to underline afterwards, the load that are in this particular structure are such high that is very difficult to carry out experimental tests. So you need basically a tool that is able to describe the fiber effect and as well is able to describe such high loads applied on the structure. And the answer for us was at that time, and also nowadays, because nowadays we are participating on the FIB task group, at that time the answer was the linear numerical simulation developed by means of Diana. Because by means of this simulation we were able to prove some spatial, global and local tunnel lining behavior, and I can tell you, as I'm going to demonstrate this presentation, we were able to answer also to some tendencies that were found in literature without a specific clarification, without a specific answer. They were able just to describe, we have this in our tunnel lines, but we didn't understand why. But with Diana we were able to prove it. So I apologize if I have to need to briefly to introduce how specifically a precast standard lining works. This is just a scheme, so I apologize because it's very simple, but I think that is clear. You have to think to the TBM, that is this one, with the shield, with the cutter rod. It is like a driller. So, as each driller, also the driller that you use in your home, when you need to use it, when you need to start the drilling process, you need a very big normal force in order to cope with the stresses that you got on the face of the TBM due to the depth of the tunnel in the ground. The only way to cope with this force is to place these trolley jacks that are basically pushing on the previous constructed lining in order to get a kind of counteraction in order to force these parts of the TBM on the ground in order to get the construction process. On the other side, you got high forces introduced by lining. And if the lining are made of FRC, you have to prove that this force can be taken by FRC. But if you have to prove, you need a non-linear behavior. If you need a non-linear behavior, you need experimental tests, of course, are the true, but are difficult to carry out, as well as numerical analysis that you can help you in develop, for instance, a parametric study. It's what we have done. Basically, we started with the Barcelona Metro Line because at that time it was one of the first examples where they tried to use FRC precast tunnel segments just to try and see from the building side what can happen. And I think, if I'm not wrong, that these are the geometrical properties of this line. And I think that is a double-deck line for a metro line. And at that time, I think that, I don't remember, but they used 12 experimental rings. So each ring is, as you can see, has a depth of 350 millimeter, and each ring, so this is a ring, is made by 7 segments plus 1 key segment. But at that time, when we were just trying to see if it's possible to use FRC, they got a problem. They got cracks. And so they decided to use a combination of fiber reinforcement plus traditional rebars during along the other sections of the tunnel lining. So they were asking us at that time why even FRC seems to be so much promising material, these cracks occur in our tunnel lining. And at that time we tried within our research group to get an answer by means of numerical simulation carried out with piano. So, besides the structural level that I'm going to describe now concerning tunnel linings, remember that a material level concerning 3-point bending test, splitting test, and bending test were previously developed in order to check as much as possible the power material. And I underline that the power material was checked also with special reference to splitting phenomena that are typical phenomena that are occurring during the construction stage. So the basic procedure was, okay, we got the concrete, typical concrete, that is concrete strength class of C50-60. We have to use this concrete in Indiana. Why don't use Torrenfeld, that is very good uniaxial compressive law that you can find in Indiana, and this law also able to use in a very simple way the so-called confinement approach. So the law can be a little increased according to a biaxial or triaxial compressive condition. And then we have decided to use this type of fiber. And so we have decided to carry out experimental test concerning this fiber. This was carried out at University of Brescia. We have decided to use this fiber reinforced concrete, but to be honest, is a steel fiber reinforced concrete because steel fiber were used. As I previously mentioned, this is the first main important step, because at the end of the step, by means of nonlinear inverse analysis method carried out by means of Diana, we are able to find a proper uniaxial constitutive law that is able to describe this behavior of this fracture bending test. And so for us, when we find this law, we are confident that this law is able to describe how the fiber works, and so we just take this law and we use this law at structural level. That for us is in precast standard segments. And this is the model. As I mentioned before, there are several stages that characterize the construction of precast standard segments. But the crucial one, the most severe, is the introduction of TBM jacks. If you remember the previous scheme, I told you that there are the jack of TBMs that are forced to push the arm of TBM. In this case, in Barcelona, there are two pairs of actuators acting on steel plate, and they are apply a quite high service load, 12 meganewton. So you can imagine that there is a very high load, which means that each jack has to introduce in the lining 3 meganewton. So it means we are talking about 300 tons. So it's quite difficult to carry out this experimental test. So is why when they ask us to evaluate how it works in the tunnel lining, the fiber reinforced concrete, we have decided to use numerical simulation by means of Diana. Here there is a long discussion that takes a lot of time and is summarized in this slide, but I can tell you that we decide to use proper boundary condition, for instance spring elements, in order to properly describe the interaction of this ring to the previous constructed ring that has been already constructed, that is already well connected to the ground around the tunnel lining. And what about the other segment of the same ring? We have used this simple no tension spring in order to simulate as a first approximation the contact behavior between each segment of the same ring. Afterwards, there is also a picture concerning the mesh refinement. We have used brick elements with two different mesh refinement in order, of course, to check, as usually is necessary, and is more than necessary when you are dealing to nonlinear analysis of cracked concrete, in order to check, of course, the results. Different type of reinforcement has been used, only fiber, traditional reinforcement with glass fiber, and then this solution that has been proposed, and I can tell you that this solution was used in other section of Barcelona Metro Line, and also you can find a paper on important researcher of the UPC University of Brescia that described that this solution has been used in several other metro lines within the Barcelona province, metro, or to be precise, other tunnel line within the Barcelona province, and was for the first time proposed by our research group by means of a numerical analysis carried out with Diana. I talk about normal loading condition because this is the general condition used by designer, where the jacks of a TBM are perfectly placed, where the contact between the rings and the previous installed ring is perfect. This is typical load versus average displacement under the loading surface diagram that can be found with Diana. As you can see, even the analysis non-linear, we got almost a straight line because we have several local behavior that make a local non-linear behavior that is very important. Even the global behavior, that is the total load versus behavior 1, it seems that remains globally linear elastic. But as you can see, it's not the case because we have several local behavior that are non-linear behavior. So we have spalling cracks between the loads and splitting cracks under the loads, as I previously mentioned. In order to properly describe this local behavior, Diana is fundamental. So we have decided for the splitting cracks and the spalling cracks that are the local behavior to check, and it is possible because Diana had us in a very straightforward way to evaluate in the very simple way how it behaves our FRC tunnel elements in that special region. And here, really, you can see at a certain point you got a non-linear behavior. This is the splitting behavior under the loads. As I mentioned before, there are the crack patterns that you were reading before that are basically cracks that are in radial direction. And you can see you got a really non-linear behavior. But because of Diana, we were able to prove that, for instance, only fiber with poor FRC, which means that is FRC with not such high properties, we got a not very good behavior, local behavior, but on the other hand, with very good FRC, we have a quite good behavior that is similar to the reference solution made by traditional reinforcement. The same tendency you got here. FRC with high toughness is good. FRC with poor toughness is not good. So after this, we were asking to ourselves why we got cracks, because here Diana said everything is going in the right direction. So fiber should work properly. Fiber works properly because we have a redistribution of stresses that we are able to prove with Diana in a normal loading condition. But probably, in our opinion, and we were able to prove, and is under discussion nowadays by the scientific community, by means of Diana, we were able to prove that probably, oh sorry, here I forgot to say that, of course, we have made a check mesh refinement, which means that all the stage, first crack, service load, 1.5 service load, and so on, was properly checked with different mesh refinement. If I'm not wrong, starting with a mesh of around, coarse mesh around 45 millimeters, brick elements, and then exactly the half. But coming back to the engineer point of view, why the fiber reinforcement in the real world were not able to properly work and they got these considerable cracks? Probably because you can have irregularities, that is, eccentricity of hydraulic jacks or inclination of hydraulic jacks. And here you can see that from this picture in the real world, you got this eccentricity. So with Diana, we were able to study these irregularities and also not only eccentricity, but also the so-called condition of missing support, also called uneven support. So something goes wrong here, so you miss one support, you got a kind of cantilever effect. Here, for time restriction, I'm going just to tell you the numerical results of an eccentric load placement of jacks. It was possible to prove it by means of Diana. And also, it was very interesting because I placed this very simple sketch by applying eccentricity. We found by means of numerical simulation that probably we got a kind of tilting. Of course, this is a large zoom of a possible displacement. In the real world, it's just a little, but is little enough to create these gaps. We were able to see this gap in Diana. And also, in this case, you got local behavior that we have described previously, here and here and here, but you should add to this local behavior a big bending behavior that probably was one of the main reason of the big cracks occurring in Barcelona. These are the results, numerical results. As you can see, we got the normal loading condition, and by applying eccentricity, we are able to prove that we have a reduction of safety, even if we are plotting the total load versus the average displacement, so it's the global behavior. But take a look to the local behavior. Sorry if I come back. The local behavior is one that I called before spalling behavior, so it's the behavior between the jacks. As you can see, in this case, by applying an eccentricity, before, in the previous slide, the FRC with low toughness was bad, so also here you got the same tendency. But also in this case, FRC with high toughness is not able to compete with a solution that are fiber plus reinforcement or fibers plus the so-called optimized reinforcement, that is the reinforcement that we have proposed. And it was also very important to demonstrate that even in a numerical simulation, and we know that there is a lot of effort to describe the real world, but of course the real world is always more complicated than expected. But by introducing a variable, a parameter that can be introducing and studied from a parametric point of view with Diana, by introducing eccentricity, we were able to prove that even the service load is applied, we got these cracks. And similar cracks appears in the Barcelona Metro Line, and so we were able to prove this possible explanation. So eccentricity could explain the presence of these cracks in presence of fiber only. And the method that we were able to let to the designer, to the people, by means of this study is, if everything goes the right way, probably fibers can be used. But if you are going to expect in a tunnel lining some eccentricity, take care that probably you can have the needed of fiber plus traditional reinforcement. And basically we were able to explain by means of numerical simulation what probably happened during the construction phase of the Barcelona Metro Line. Here I have placed just very briefly, and I'm going to close, some other example, because you can have also other possible explanations that are the gaps. And so we have studied other metro line. This is, sorry, it's not a metro line, but it's a railway line, Italian one, that is Mappa and Saronno. And we have studied also by means of Diana the possible condition of missing support, very unfavorable condition. As you can see, it's very severe. But by means of Diana, we were able to prove that by means of numerical simulation, only traditional reinforcement or opportune reinforcement concentrated in these two chords, plus fibrous reinforcement, fiber reinforcement, you can get a better behavior by means of fiber reinforcement. And that was proven by means of a well-validated simulation, because, as I mentioned before, all the starting point was a properly check of our confidence as user with Diana and this very advanced crack model. So I hope that this presentation can be appreciated, and I thank you for your kind attention, and I let you the time to let me know some feedback and so some questions. Thank you so much.